Hello, everyone. Today we'll be discussing the second law of thermodynamics and heat engine efficiency. This topic explains the limits of energy conservation and why no machine can ever be perfectly efficient. We'll also explore real-world examples such as car engines, power plants, and refrigerators. So thermodynamics is the branch of physics that studies heat, energy, and energy transfer. The first law of thermodynamics states that energy cannot be created nor destroyed. However, the second law explains that although energy is conserved, not all energy can be converted into useful work. This law places limits on efficiency in all energy systems.
The second law of thermodynamics. The second law of thermodynamics states that heat naturally flows from hot objects to colder objects. Reversing this process requires external work. This means that energy transfers have a natural direction and many processes are reversible. A simple example is a hot coffee cooling down over time. What is a heat engine? A heat engine is a device used to extract heat from a source and convert it into mechanical work. Heat engines contains three major components: a heat reservoir that supplies heat energy, the engine itself, which performs the work, and a cold reservoir that receives waste heat. Examples include car engines, steam turbines, and power plants.
So this is a diagram trying to visualize how heat can be dispersed into work as well as what gets turned into work and what gets wasted as heat energy. So the heat engine absorbs heat energy represented by QH from a hot source. Part of this energy becomes useful work represented by W, and the remaining energy leaves as waste heat represented by QC. This equation shows how that useful work equals the heat absorbed minus the heat rejected in the surroundings. Because some heat must always leave the system, complete conversion of heat into work is impossible. Efficiency measures how effectively an engine converts heat into useful work. Higher efficiency means less energy is wasted as heat energy, and efficiency depends on reducing the amount of waste heat released into the surroundings. However, according to the second law of thermodynamics, waste heat can never be completely eliminated, meaning QC can never equal zero. This is why no heat engine can ever be 100% efficient.
Here's an example we have of the second law of thermodynamics. In this example, a heat engine absorbs 800 joules of heat energy and rejects 500 joules as waste heat. So 500 joules is not used at all within the calculation. First, we calculate the work output by subtracting the waste heat from absorbed heat. This gives us 300 joules of useful work. Next, we divide the work output by the heat absorbed to calculate efficiency. The engine is 37.5% efficient. This means that only 35.7% of the input energy is converted to actual useful work. The remaining energy is lost as heat. The reason why 100% efficiency is impossible is due to the second law of thermodynamics, which requires that some heat must always be rejected into a colder reservoir. Because QC must always be greater than zero, no engine can ever reach 100% efficiency. If you see this diagram here, it's almost a cycle. And within that cycle, heat is always lost as energy. So energy is always lost as heat or sounds, which can be done through these engines. Because of that, because of the second law of thermodynamics, this cycle isn't completely perpetual. It will always eventually die off.
So, as you know, refrigerators are doing the opposite. They want to cool down instead of heat up. So, refrigerators and air conditioners work as reserve heat engines. Instead of converting heat into work, refrigerators use work to move heat from colder areas into a warmer area. So, since this goes against the gradient, it actually requires work and energy to be put in order to get that waste removed. This process requires external energy because heat does not naturally flow from cold to hot. The refrigerator removes thermal energy from the inside of the system and releases it into the surrounding area. So here we have some real world applications. The heat engine principles apply to many technologies used every day, including automobiles, jet engines, steam turbines, and power plants. Most power plants operate about only 30 to 40% efficiency, meaning a large amount of energy is actually lost as waste. Engineers continuously work to improve efficiency in order to save fuel, lower operating costs, and reduce environmental pollution, which is a key factor in today's society, where environmental pollution is a huge factor as well as the economy and fuel prices continue to grow. This is going to be something that's very important.
In conclusion, the second law of thermodynamics explains why energy conversions are never perfect. Heat engines convert thermal energy into useful work, but some energy must always be lost as waste heat. These principles are important to understanding modern technology such as engines, refrigerators, and large-scale energy systems. Understanding thermodynamics also helps engineers develop more efficient and environmentally friendly technologies. These are our references. Thank you for your time.
Thank you for your time.